Okay, so now that we've gone over the different symmetry elements, we are in a position to talk about point groups. And so to remind you, point groups are the set or a set of symmetry elements and operations that describes the overall symmetry of a molecule. So it's all of the different rotations of the inversion center, reflections, and the identity operation that a given molecule has. Okay? And so it turns out that all molecules fall into one of about 50 point groups. I say about, it's because mathematically there are infinite point groups because you can have some crazy high rotate, you can have, a crazy high rotational axis. For example, you can have like a C100, but I don't know of any molecule that has a C100 in it. You'd have to have 100 atoms, arranged just so. And yeah, I don't think that exists. So that's why I put about 50 because although there's infinite point groups mathematically, only about 50 are relevant for chemistry. Okay. Some point groups have only a few operations. For example, there's a point group called C2b, and that has only 4 operations. It has an identity, it has a C2, principal rotation axis, 180 degrees. And it has 2 mirror planes. Here I've distinguished them. One I've called sigma v, the other sigma v prime. But they're both they're in 2 different locations, but they're both vertical mirror planes. Okay. Other point groups have many, many operations. The IH point group, which stands for icosahedral, has 120 symmetry operations. And there are molecules that fall in this icosahedral point group, or even infinite, like the point group called C infinity V. This is for like a linear molecule. Okay. Within a given point group, all symmetry operators whose elements are similar, there's a rigorous definition. Roughly, it's transform. They can transform into one another. We're not going to go over the rigorous mathematical definition, but for us, it's all symmetry operations whose elements are similar. Okay, form a class. So what does that mean? Like certain types of rotations will probably go together. Like all C4s might go together, or all C2s might go together, or all sigma Vs might go together, or all sigma H's, or all sigma Vs might go together. E and I always form a solo class. So that means identity, there's no other operation like it, right? The identity was just itself. You can't have multiple identity operations. So it's no other as operations like it, so it's in its own class. And then version operation is in the similar category. In some sense, inversion and identity are sort of similar. It's just they're kind of opposites of one another. Identity is taking XYZ and going back to itself, XYZ. And inversion, remember, was taking XYZ and going to negative X, negative Y, negative Z. So they're kind of similar, and they're both similarly unique in that way. Okay. There's 5 different general types of point groups. There's the linear point groups. Those have infinite symmetry operations, as we'll see. There's other ones that are of very high symmetry. We tend to group those together because they're not super common. Or if they are, they're pretty easy to identify. So those are like tetrahedral, octahedral, and icosahedral. They're the C groups. These are molecules that have rotations, but they don't have any perpendicular C2s to that rotation, that rotation or those rotations. And then there's the D groups. The D groups have rotations, and they also have perpendicular C2s. And it turns out in 3-dimensional space, if ever you have one perpendicular C2, you're always going to have n perpendicular C2s. So if you're in a D group where the principal rotation axis is at C4, you will have 4 perpendicular C2s. If you're in a D group with a principal rotation axis of, let's say, C5, you will have 5 perpendicular C2s. And we'll see examples of this in a bit. And then finally, there's sort of oddball ones that are of very low symmetry. These point groups maybe just have the identity, or just have the identity and then one mirror plane, or just have the identity and an inversion center. So in order to give the names to these point groups, you want to use a point group flow chart. There's one in your book, there's one here. You can find many different ones online. it doesn't really matter which one you use, but you better get the same answer, and you will if you're using it properly and the flowchart's valid, which, I think most of them online are valid. And so just let's look at this a little bit. How do you go through this? This flowchart first asks you, are you in a special group? Well, what does a special group mean? A special group means you're either linear or very high symmetry. So if you say yes, you're going to go down here, and that's going to ask you, are you linear? And if you say yes, then you're going to be C infinity V or D infinity H. These are both linear molecules. The D, though, has a perpendicular C2, actually has infinite perpendicular C2s. The C infinity V doesn't have that. D infinity H also has a sigma H. That's why it has H in its name, but knowing the difference between D and C is important, okay? If you say, no, it's not linear, you're going to go to very high symmetry. And if you're asked a question, is it very high symmetry? No. Okay, if it's not very high symmetry, there's only 3 options that aren't covered by these other ones. Okay, C1 is a special point group that only has identity, so that's usually pretty easy to figure out. CS only has identity and 1 mirror plane, and then CI only has identity and the inversion. Okay. If it is very high symmetry, it's either going to be usually IH, OH, or TD. Okay, those are normal, like an icosahedron has IH symmetry. An octahedron has OH symmetry. A normal tetrahedron has TD symmetry. These T, THs, O's, and I's are incredibly rare point groups, and they're ones that have some broken symmetry, but most of the rotational elements. So like TH has a sigma H, but it doesn't have the sigma D's in it. T has, T has all the different rotations that a tetrahedron has, but it doesn't have any mirror planes. O is analogous for octahedral, and I is analogous for icosahedral. But really, what I want you to focus on, and maybe I'll highlight these on the slides. I want you to know, IH, OH, and TD, because those are, like I said, for a normal icosahedron, it's going to be IH. A normal octahedron is going to be OH. A normal tetrahedron is going to be TD. So these are way more common than other ones. I want you to know these, okay, and these as well. All right. Now we can go to the case if we said we're not in a special group. So the first thing we need to ask is there a C2 perpendicular to the principal rotation axis? That's what CN means, principal rotation axis. Remember the rotation axis with the highest number, so like a C6 or C4, something that's the highest in the molecule. If you answer no to that, then you're asked, are there any mirror planes? And if you answer no to that, you're going to be most likely a CN. CN only has a rotational axis, okay? Or you're going to be an SN, which only has an improper rotation axis. SN is pretty rare, but the CN and SN both do exist. I'll show you some examples of those. Okay. Now, if instead you said, no, I don't have any perpendicular C2s, but I do have a mirror plane, much more common, then you're going to say, do you have a mirror plane perpendicular to the principal rotation axis? If no, it's going to be a CNV, so like C2V or C3V. If yes, it's going to be CNH. Okay. If you are not in a special group and you ask this question, do I have perpendicular C2s, and you answer yes. If you don't have any mirror planes, you're just going to be in this pure dihedral group, DN. But if you do have mirror planes, if they're not perpendicular, if there's none perpendicular to the principal rotation axis, it's going to be DND. And if you have a mirror plane perpendicular to the principal rotation axis, it's going to be DNH. So, this is a language, guys. And so just like any other language, I threw out, when you're learning a new language, you get thrown out a lot of new information at you at once. And so it takes practice, right? You just got to practice, and it'll become a second nature to you as you do this more and more, and as you go through more practice. But you got to practice on these. We'll do some practice together. I'll show you some good ways to practice. It takes some visualization skills. If you want to buy a model kit, or if you have access to a model kit, that is a good idea. There's some resources I'll show you in the next video online that are very nice. If you don't feel like buying a model kit, you know, what I use is I use marshmallows or gummy bears and toothpicks, and that works actually pretty well. It's super cheap, right? Cheaper than buying a model kit. And you can do like crazy coordination chemistries that you can't do, coordination geometries that you can't do with you know, the commercial model kits. So that's kind of fun. So yeah, one other tip for this, you know, there's a lot of D's and C's and H's and V's and all this stuff. One tip you'll notice here, there's CNV groups, there's DND groups, but there's no DNV groups and there's no CND groups. So how do I remember that? A quick way I remember it is that there's no CDs or DVDs. Okay, so there's no CD groups and there's no DV groups. So I remember this mnemonic I made up. There's no CDs and there's no DVDs. All right, so we'll do some, actually I'll show you the website I really like next video, and then we'll do some practice after that.